Imagine that you're in charge of a software company, and you're about to hire a new developer. The recruitment process is down to 2 applicants, and you're browsing through their code repositories. The first guy has 2 versions of the same to-do list application, but the other guy has got something different. He has written a small operating system, completely in JavaScript. Today that guy will be you, with the help of Dr. Jonas. And you are allowed to use it on your GitHub and your CV.
Sup guys, welcome to today's show. So today we're going to code an operating system in JavaScript. A small one, but an operating system nonetheless. I have created an empty folder and just initialized this project. And I created a main.js. And we're going to start with defining I'm going to create a function for each of the machine code instructions. So let's say we have an object which I'm going to call CTOR for constructors. Maybe CTORs actually. And CTORs is going to be equal to an object and here we're going to have different instructions. So what do we need to do to boot a computer? Well, the first of all, it works like this. The BIOS, which is the circuit which does this starting up process, it is going to open up the first hard disk drive, if that is the first one in the boot order, and then it's going to take and read 512 of the first bytes on the disk, and it's going to store this at the memory location of FC00. Then it's going to look at the last 2 bytes of these 512 bytes, and that is the so-called magic string. It's a verification that the disk is actually bootable. So if this contains the special signature, which is AA55, then it's going to start executing the code, beginning at the start of this 512. So basically it's going to jump to the address of FC00. Alright, so what we need to do is create, because I'm going to create the hard disk drive, and then we can launch it in a virtual machine. So basically we're going to need to create a 512 byte file containing the machine code instructions that are necessary. And which are those? Well, we're going to have something which initializes the stack. So there is something called the SP, the stack pointer. It's a CPU register, and a CPU register is a very primitive form of like RAM memory almost. So it's just a couple of circuits which form binary digits. So it's either leading voltage or not. on or off, 0, 1. And SP is a 16-bit register because the all x86 CPUs start in the 16-bit mode for compatibility reasons. So the SP contains the stack pointer, and we need to have a stack initialized. So we're gonna have to have an instruction which does, we have to have two instructions actually. We have to copy a value to the AX register. That is a general purpose register that we use as an intermediate thing. So we need to select an address for the stack, move it into AX, and then we copy from AX to SP. And then we have a stack. Then we want to print our message. So let's see, this is number 1. Initialize stack. Number 2 is we want to print the message. And we're gonna use the BIOS to help us with that. So we can make a type of system call by telling the BIOS that we want to do a specific thing, and there is a long list of different things that the BIOS can do. In order to do that, we need to copy values to registers again. So we need to copy stuff into the AX, BX, and possibly CX register. And we're gonna have to, let's see, well, when we have the right values in the right registers, we're gonna execute an interrupt, which basically leaves the control to the BIOS. So the assembly instruction for that is int 0x10. So that's what we need to mimic. So if we're gonna name our different instructions, so let's say we have copy to AX. So this is 1. And also copy to SP. So those are the two that we need here. And here we need to copy to AX, BX, maybe CX. And we need to issue the, let's call this BIOS interrupt. And when we can print the message, we need to halt the computer. And you do that by doing 3 things. First of all, you disable interrupts, so it will not interfere with this halt. You issue a halt instruction, and if that fails or if it breaks out of it, we do an infinite loop. So these are all the different building blocks. And how are we going to figure out what machine code to do? I have an idea, so I'm going to show you that. But let's first define the general structure for our constructors. So let's see. so the first thing we're going to do is copy to AX. So we'll have a copy to AX, and this is going to be a function that takes in the value that we're going to copy. So val, and then we need to return the opcodes, so the machine code. So something like 0x90 plus val to string, or something like that. We need to experiment a little bit, but something along those lines. So let's just do void 0 for now, and we're gonna have copy to SP, and this is going to be, we're gonna make it so it always copies from the AX register, which means we don't need an argument for this. And then what? Well, we're gonna copy BX as well, so let's do one for that. Copy to BX, and this will be the same syntax, val to void 0. And we'll wait with CX. I'm not sure if we needed that. I don't think so. We're gonna check the specification. And then we need to do the BIOS interrupt. So BIOS interrupt. And this is not going to take any argument. Okay. And then we just have this infinite loop kind of thing. So let's see. Alright, so we need to be able to disable the interrupts. So disable interrupts. Let's call it interrupt off. And this is not going to take an argument. And by the way, those void zeros that I put here, that's just a temporary placeholder. So issue a halt instruction. Let's just call it halt. It will not have any argument. And infinite loop. So basically we need to, because you do an infinite loop like this in assembly. So you set a label, so something like this. So this just says that this is the name of this current memory address is called halt. So it's like go-to in C, or basic, or any language. Alright, so then we need to have some instruction in between. It's not strictly necessary, but I think it's good style. So we can have a no-op, which is just an instruction that does nothing. And then we jump to this halt. And we will also issue the actual halt instruction. So this is our infinite loop. And those will be static machine code, jump as well, but this label will be a memory address or an offset to it. So maybe we need to calculate a little bit. We'll see how it goes. But we'll call all of this. Well, since we're going to be using, we need to use this jump here as well, because when we print, we only print one character, so we need to loop this with the help of a jump, which also means we need to have the CX register as a counter. So let's add this CX here, and so we'll have a halt, but we'll also have a jump, which is going to take a memory address and return that machine code. Right. And then we are done. Then we just need to write the where did I save this? I didn't. Well, the magic string. So this needs to be at the end, and we'll need to have some padding in between also, because these will not be 510 bytes. These will be, I don't know, maybe 30 or something. So we're gonna have to have some padding, and we need to know the amount. So so let's have an amount, and this will return the padding, and then the magic string. No arguments, returning the magic string. And this is the entire thing. Then we just need to figure out how we write the stuff to a file. Okay, so how do we know how we copy something to the AX? What's the machine code for that? Well, we can use two strategies. Either we can use a disassembler, which will show us the assembly code together with the machine code instructions. Or we can read the Intel manual, which is pretty dense. So I will use the first strategy. And I have created an alias. So if we do alias objdump, I have this. You probably don't have this. And also I have an objdump 86. So you can copy this thing and just paste it in like this and press enter. And now you can use this objdump command. And it needs to be this 86 version, because we are working in 16-bit mode, and that's a different instructor set, kinda. So that's why. Alright, so if you don't have NASM installed, install it. If you run Windows, you need to download NASM and install it. If you run Mac OS, you can do brew install NASM if you have homebrew installed. And if you don't, you need to install homebrew first. And in Linux, we can just do sudo apt-get install NASM if we run a Debian system or something similar. Otherwise, you use your regular package manager. Okay, so let's go into VS Code. And let's create this temporary assembly file. So let's call it temp.asm. And let's do a couple of these. Step 1, where we just copy to registers. So we're going to work in 16-bit mode. And we want to know what, let's say, move into AX and the value So let's see, we are going to use 16-bit value here. So let's do something which is 16 bits. So something like AABB, so it's easy to locate. And then we do the same for BX and CX, and we also want to know what move into SP, the value from AX. So these are the four that we have already talked about. So let's compile this, or assemble it as it is called. So we run nasm-f-elf tmp.asm, and let's see, now we should have this O file, and I think we can run objdump directly on the O file. So objdump 86 tmp.o, and here we get a whole bunch of stuff because it has headers and other things. But I think in the beginning that we have our code. Nope, it's not in the beginning. Okay, so well, let's just do this. Let's see if we can find our AX, BX, CX stuff. Here it is. So as you can see, the AX didn't get here, and that's because it reads it a little bit bad. So we can fix that by isolating the instruction with a couple of no-ops. So we just encircle this in no-ops, and no-ops just mean no operation, it doesn't do anything. And we need to recompile, so nasm, and then we run this again. And maybe we can even do something like grep-3 move, maybe. So let's see. Okay. Sometimes this is a little bit messy when we do it like this. So let's add some zeros here as well. So dd0, and same here. I wonder why it does this. It's usually not this annoying. What happens if we put another move to the BX? What happens then? Ah, here it is. Okay, that's good. So this is the assembly instruction to move this value into the AX, and if we look to the left here, we see how this works. So we have the AA and the BB in reverse order. And then we have B8. So B8 means move into AX. And if we look at this BX example, it's the same, only this is BB. And for the CX, we have B9. So B8, BB, B9. And copy this. And then we go to VS Code. And let's paste this in a comment here. Alright, so in order to copy to AX, what we need to return is a string where we have the hexadecimal value B8. And then we have the value. So this should be encoded in hexadecimal. So how do we do that in JavaScript? I'm not really sure. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support. Sup guys, welcome back. So let's create this reverse function. So rev is going to be a function that takes an input value, let's say val, and returns something. And how do we do this? Currently we have a 16-bit number in the wrong order. So let's say it's something like this. So this is 1 byte. Let's, for sake of simplicity, say that we have something like this. Okay, so this is our number. Doesn't matter what kind. What we need to do is we need to divide this into 2 parts. So let's make this explicit, at least from the beginning. So let's do something like this. We will have 2 numbers, A and B. And let's say this is the B number and this is the A number. So first of all, we want to isolate this A number right here. And we do that by something which is called masking. So basically we create a third variable. Let's say we have that here. So we have those 2 and we'll have the mask. And a mask is a number where every 0 means it's not selected and 1 means it is selected. So if we create a mask that looks like this, this means that we have selected this part. All right? So that's what we'll do. And we'll use the AND operator in order to select. So first we need to set this mask to something which corresponds to 8 1 bits. And this is the hexadecimal representation of that. So let's say that our a variable is equal to, and we take the input value, the 16-bit number, and we AND it with a mask. And now we have isolated this part. All right. So far everything is good and well. But how do we grab this part? Well, we need to create another mask which looks like this, right? And then we select this part. But the problem is, when we use this kind of selection, we will get these bytes, so 0, 1, 0, 1, 1, 1, 0, 0, but this part will be filled with zeros, so this will be a large number with a lot of 0 bits at the end. But let's start there. So let's do this. Let's create an intermediate variable. Let's call it I for intermediate. And we do this masking. So let's change this mask. And these should be ones and these should be zeros. So how does a mask like that look? Well, it's 0xFF 0, 0. So that's that representation. And then we do what we did before. We set our intermediate variable to val and mask. So now we have this, but we have all of these zeros at the end. So we need to use another operator, which is the bitwise shift operator, or the right shift operator. And if we do this and tell it 8, that means that we should push this 8 positions to the right. And everything that falls off here gets removed. And that is exactly what we want. And then we're left with just this. So our B is going to be equal to our intermediate value shifted 8 times. And now we have those two. But what are we going to do with these two numbers? We want to make like a string out of it. So we need to take their ASCII representation and make a string. So what we'll return is, let's see, we want to have, we want A to be first, right? So we'll do A, and then we'll use, first we need to turn it, let's see, I think we need to turn it into a string. And then we need to use no, we need to do string from char code, and we provide the A. And then we concatenate this with string from char code of B. I think this will be the right thing. because what we want to produce is B8 followed by, let's see, if we have the number AABB, or let's say CCDD, we want this to be DDCC, okay? And I think we are at that point now. So let's change this to CCDD. And let's try it out. So we'll run this and we get this weird output. But we need to check the hex representation. So we take the last line and we put it through our hex dump. And we get this. We get a lot of strings, things. Let's count the characters. Is it C? 7 characters. Let's see, we have the string B8 plus this string. X is this, Y is copied to AX, X, and we console log. Perhaps we need to explicitly tell it to be because we want each of these to be an 8-bit number. So let's reset our mask to what we had from before, this. So we only take this last part. Maybe that's a problem. Let's AND this with a mask, and we AND this with a mask. Will it still be 7 characters? So what do we have? We have the B8, we have the CC, let's do we'll reset this. And let's do a console.log. So we have A, and we have A. And we have B. So A is 221, B is also 221. And what is 221? Okay, so that's 0xdd. Oh, forgot to change it. Okay, so we do get the right numbers. And if we were to console.log string dot from char code of A, it's a little tricky to see. Let's grep only that line. And remove this. And what do we have? It's a little bit weird. I wonder if it has something to do with us printing it. Might be. So let's say if we remove this and instead of console.logging this, we create another variable, z, where z is equal to, and we take this y and we turn it into an array, and then we map through this array, which means we get an A, and this A we take the ASCII number. So let's see, char code at something like this, and then we console.log z. So this should be an array of numbers. Okay, it seems to work. It probably has something to do with the printing. And let's double check that by putting this back, and I want to see the length of this thing. It should be 3, right? Okay, yeah. So it has something to do with us printing it and then piping it to hexdump, but it seems to work. By the way, the order, did that work? So we have CCDD, we want the DDCC. And which one is first? Let's take the hex of this. So DD is first. Yeah, it works. Okay, good. Now that we have this function, the rest would be pretty easy, at least some parts of the rest. For instance, if we move this down, copy to BX and CX will be pretty much the same. So B8 was AX, BB is BX, and B9 is CX. So we'll just do the exact same, only we changed the first byte. So something like this, and then B9. Okay, what about the copy to SP? Let's go back to this and let's do stuff a little bit differently. I'm gonna set the org to 0xFC00, and I'll explain that in a little bit. But first we want to figure out this move. So what we want to do is we want to move into SP AX. And let's just do this. And let's compile this a little bit differently. Let's remove this O. And we're going to run NASM, but we want to create a bin file instead. So we'll take our tmp.asm and produce tmp.bin. And the bin file we should be able to run objdump on and only get this part. Alright? So this move is 89C4. So copy to SP, only thing we need to do is return the string 89 followed by C4. Alright, so far everything is pretty easy. It gets more complicated though. We need to remember the comma. Okay, so our copies are done. Now we need to do the BIOS interrupt. And the instruction for that is int 0x10. And this can be different things depending on what system calls we want to call. But everything that has to do with printing on the screen and stuff like that is the BIOS interrupt 10. Right, so we save this, we run NASM, and we run objdump. And this is CD10. So our BIOS interrupt is CD followed by 10. Okay. And our next thing is to disable interrupts. And the machine code for that is clear interrupts, like so. So we do the same here again. So FA. So we simply return FA like so. Then we come to a little bit more difficult stuff. Well, the padding and magic is pretty simple. The halt and the jump, not so much. So let's start with the easy ones. Let's do the magic string. And the magic string is 0x AA10, let's see, AA, now I completely forgot. Is it AA10? So boot sector magic number. AA55, okay. So 0xAA55, which means we're gonna make it 55AA, since we need to reverse all numbers like that. So the magic will return a string of x55 xAA. Or we could have done rev 0x AA55. This is a little bit cleaner, I think. Okay, it's no problem. What about the padding? So this should return either we do 0 bytes, a couple of those, or we can do 90, which is the nope instruction. So let's do 0 bytes. It doesn't really matter actually. All right. So how do we create a repeated pattern, and how do we know how many we need? We're going to push the amount here. So first off, we only need to figure out, let's see. Well, first of all, we only need to repeat the pattern. And I think there is a string function for that. So if we say that we have this 0 byte thing, and we just do a dot, then we have this repeat. And it just takes as an argument how many we want to repeat. And I hope it works on 0 bytes. It's not 100% sure. Maybe we should do 90 just to be certain it works. Okay, so this will provide as many as we need, but how many do we need? In order to know that, we need to do the other ones first. But we know how many, we need to know how many bytes all of these are, and then we can do this. So let's leave it like this for now. And magic string is done, this is done. Now we come to the halt and the jump instructions. The halt is pretty simple. That's actually just one instruction, or two in our case. So we're going to do the no up, and we're going to do the halt. So we can use the same strategy as before. 90 F4. F4, like so. Okay. But the jump is a little bit more tricky, because when we jump, we need to provide an address where to jump. And that depends on where we're at in the memory, and it's also dependent on, like, it's a relative thing. How far should we go? So if we go to the assembly and we put this together, like so, and we create a label. So let's say this is our halt label. So we wanted these two, and then we want to do the jump to our halt label. And if we check the assembly of this stuff, it looks like this. So we do a jump to the address 0, so the beginning of the program. But this is what it emits. So EBFC. What if we were to repeat this? And let's call this halt 1 and halt 2. Okay, I don't know what happened. Let's do halt 2. How does this assembly look? Right. So EBFC is a jump to 0, and EBFC is a jump to 4. What if this second label also wants to jump to halt 1? Will that change anything? Okay, so here we have EBFC. Here we have EBF8. And that's what I mean by it being relative. So when we jump the same number of steps backwards, it becomes the same thing. But now we jump, double the distance, and it becomes F8. So I guess it starts at FF, and then it decrements the number of bytes. So the jump instruction here is at, or let's take this one. The jump instruction here is at byte number 2 with a 0 index. And when you jump to 0, so this is 2 bytes back. And if we take FF minus 2, so E, D, C, okay, it's minus 3, because we're here, and we want to go 1, 2. But this is not a problem, actually. Do you understand why? Because as we have demonstrated, it doesn't matter where in the program we are. The only thing that matters is how far back are we going to jump. And since we know that we're going to have a no up and a halt, and then our jump instruction backwards, that means we know that it's going to be precisely EBFC. So this is actually not a problem. So our jump is going to be X EB X FC, like so. All right. So let's see. let us now do this. Let's say we have a function which is called makeOS. And makeOS is a function which takes no arguments. By the way, we have cheated a little bit. Well, we did the BIOS interrupt, but we haven't used this part. And we need to take that into account when we make this function. So makeOS is going to return a string. Let's do it like this. So first of all, we need to initialize the stack, which means we need to first copy into AX. And what do we want to set the stack to? We want to set the stack to anything which comes, let's see, the stack grows towards lower memory addresses. So if we were to set the stack somewhere here, it might grow and alter our code. So we want to set it before everything else. And since we know that the BIOS will read this code into the memory segment of FC00, if we were to set the stack pointer to this -1. So basically that should be a B here instead, and FF. If we set it to this, then we are sure that we're not overwriting any data. So let's do that. So into AX we put FBFF. Let's do like this, and then we add the instruction to copy from AX to stack pointer. So copy to stack pointer, no argument. And what are we going to do next? We want to issue this BIOS interrupt, but before we do that, we need to tell it what to do. So we need to go to the manual for BIOS interrupt. So we search for BIOS interrupt 10. And we can go to, this one is good. So here's a list of all the different BIOS services on section 10. And the one we are interested in is this one. Write a character at the current position. So here it says what we should put in the different registers. And they have divided the AX register into a high part and a low part, each 4 bits. And so we need to take that into account. So in the lower part of the AX, we put the character in ASCII, that we want to write, and AH should be 0A. That basically just selects the type of system calls. And into BH we select the page, and we're only going to have one page, so that will be 0. And into BL we set the color, and we'll just use a 0 that too. So we need to move a 0 into BX. We can start there. So we move into BX 16-bit 0. And maybe we, let's see. Yeah, that's good. Okay, so we moved into BX and CX count of characters. I wonder, is this really the right one? Here it is. This is what I want. Because this only takes page number, foreground pixel, so this should be 0 as before, and then we only need to provide the character and this. So this is what we want. So we need to do a little bit of bit shifting here so we can combine this two. So let's see. So let's start with printing one character so we know that that works. So let's say we move into AX and we want to provide a number which is 0E and then the character here. Let's say we have a function combine, and we want to combine 0x0e and our character. So let's say, I don't know, x. And what is this combine thing? So combine is going to be a function which is going to take two variables, a and b, and this should be 8-bit bytes. Okay. And what do we want to do with these? Well, we want to take So A is the higher part. We want to take A and we want to shift it 8 bits to the left. So now we basically do the reverse thing here. So we shift this 8 positions to the left. And then we just want to combine it with a B. So this time we do an OR operation with a B. And that should work. Let's also make sure, let's say we do this, we AND this with a mask of FF, so we make sure that it's 8 bits. And same here. Probably not necessary, but let's do it anyway. Okay, so this will do the right thing. So now we have prepared our registers. Now we just need to issue the actual interrupt. Like so. And now it should have printed something to the screen. And now we just want to hang everything. So we will issue our halt. By the way, we need to prefix these things, right? Like so. So we'll run our ctors.halt. And that includes the no up. And now we want to jump to that. So we don't need an address here, by the way, since we always jump the same amount. So this would just be ctors halt. And then we need the padding and then the magic string. So let's say we have a part 1 and we have a part 2. So instead of make OS, this is part 1. And part 2 is our padding. And we need to know the amount here. I'll just set the 1 for now, temporary. And this should also be ctors. And to this we add the magic string. And let's say that this takes an argument, the amount of padding. So we put this right here. And now we can make our OS. So make OS is going to be a function that runs ctors dot, no, it runs part 1. And then we add part 2. And what is the amount here? Well, it's a calculation where we start at 512, and we know the magic string is 2 bytes, so we can remove that. So 510 minus part 1. So minus part 1 dot length. That is our length, so to speak. The amount of padding that we need. Okay, I think this is going to work. At least for one character. But how do we test this? Well, we need to write this to a file, which is going to be the hard disk image. So how do we write stuff to a file? We need to open the file first. So we need some kind of file descriptor. And I guess we need an import of some kind. Let's see if I can remember. We need something which is called open file, I think. And we need it from node. Node. Can it be file system? It's something with a promise, I think. Node fs promise. Let's test inside of the interpreter. So we go into node. And we try to import open file from node fs promise. Okay. Const blah 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 is equal to await import. Didn't I type just that? Apparently not. Unknown module. Okay. So promises. Okay. Okay, so how do I remove that? Can I just say delete open file? False. Okay. Open file as open file 2. Okay, so there's no node promises. Because if we just do this, undefined. find. Maybe we can check the manual. It's not cheating if it's the official manual, right? So Node.js open file promise fs promises.open. But this is the wrong thing. Here is the official manual. Open file. Okay, just open. fs promises. So if we try this again, open is equal to await import node fs promises. There should be a slash. Node fs promises. Okay, so fs slash promises and a colon there. And there we go. Okay, that's good. So let's fix this before I forget it. So node fs promises. So we need to open the file and then we need to write to it. Let's see. Equal to await open here is not right. Here. So it takes a path, some flags, and a mode. So let's create a function. Save to file. Save to file is equal to an async function because this is asynchronous operations. So an async function that takes in a file name and does something. So here is where we need to have the fd. Let's remove it from this. And fd should be equal to await open. We open the file name and we want to write to it. And we need to write with permission 644. this fails. Like so. Otherwise, we want to write our stuff. So let's create a variable buff, and buff should be equal to make OS. And how do we write something to a file? I guess there should be a write method as well inside of the promises API. Write file. Maybe that's better. It takes file name or file handle, okay? And it takes the data and it supports a string and options, encoding, mode, flag. Well, I think we only need the file and the data. So, and maybe some return value. So return value should be equal to write file, and this needs to be awaited. And we give it the FD, we give it the buffer. And what does it return? A promise that fulfills with undefined upon success. Okay. It's a little bit odd, but sure. So if the return is not strictly equal to undefined, then we throw. But before we do that, we want to close the file. And we want to close the file no matter what. So let's just do that. Close FD. Let's go to the top and open, close, and write file. I'm going to throw a new error. Unable to write to file. And then we return true, perhaps. So let's say we have an exit val. Exit val is equal to a new boolean, and we take the save to file. And what do we put here? The file name. We would like to read it from standard in, but how do we do that? And not standard in, I mean the argument list. Process.argv. Let's just do this for now. And I want to try that out. So let's say we have an x. X is equal to process.argv. I guess this is an array. Something like this. Cannot use import statement outside a module. Set type to module, okay. It's kind of weird that affects the built-in modules as well, but okay, how do we close the file then? Isn't it a method for closing the file? Okay, it is. It's just not. Okay, it's on the file handle itself. I keep forgetting this is an object-oriented language. So this should be fd.close. Save to file. Alright, let's see. So this is what we get as a command line argument. If we run node dot is okay. Okay, so we get this and this as two parts of the same thing. Okay, so let's do 1 and 2. And if we type something here, Okay. So let's say we have a let's say we have a file. And the file should be equal to process.argv2 if file is empty, and we want to print usage followed by process.argv1 and then the string file name like this. And how do we exit? Process.x. It must be process.exit, right? Okay. And maybe we could add a hashbang to this. Or let's not bother. Okay, so now we have the file name. We can call this thing with our file name. And if we have a good exit val, console.log, okay. Otherwise, console.error failed. But this save to file is an async function, right? So we can't really take care of the return value. Unless it's possible to do, let's not do this. I don't think we can do just a wait at this level, but let's try. And let's say os.bin. File name is not defined. It should be called file.
We did not get an error on the await though, did we? Move to bx is not a function. Then what is it? Copy to bx. Okay. And we did get something, but it's far too big. So that's one thing. But what does it contain? If we were to do a hex dump, undefined, undefined, okay, that should not be there. I wonder which one that is causing that. We haven't tried our combine function, but maybe we need to translate this into an ASCII character. So we have the X and we want to shortcode at 0. Maybe that is why it's weird. Still far too big. Okay, so here is the X. And then a couple of dots and undefined, undefined. So this should be fine, I guess. Interrupt off. And we have 2 halts. Why do we have 2 halts? And a void here. Okay. And after the halt, we should have the jump. Okay, now I think it's better. It grew even bigger. Here are the 90 that we want to pad with, but it pads with both C2 and 90. That's weird. And same here, we have the AA, but C2, 5, 5. What is a C2? $194. It's one of these weird characters that we had before as well. Maybe this has to do with the encoding. I think I remember that encoding was a part of this write function, write file function. File data options encoding. A string or null, and the default is UTF-8. Maybe this C2 is a UTF-8 kind of thing. So what do we want to have instead of UTF-8? Is there one for just regular ASCII, or how does it work? Wonder if the manual says something about it. Encoding can be any one of those accepted by buffer. uint8 array. So what if we were to make it a uint8 array instead? And from hex. Well, we can try it on the magic string to begin with. Or no, we probably need to have everything in that. Let's try first with writing it. Where is it? Write file. So if we add an options object and we say encoding none. Okay. What about ASCII? Okay, that went through. Huh, 512. Look at that. All right, looks good. Let's see if we can run objdump on this thing. Okay, so what do we have? We initialize AX and move it into SP. So we have a stack. We move to BX0 and we move into AX. This is not right. E7, 8. Let's see, we're gonna print the character X. So that is 78, okay. And the other one should be 0E, but it became just the E. Combine 0x, 0e with the x. And we take this, push it to the left. Ah, wait a second. It just prints it this way. There is a 0e here. It just removed the initial zeros. So that's no problem. All right. And then we clear the interrupts. We don't do the int instruction though. Nope, we forgot that one. So we need to do BIOS interrupt. Like so. So let's write this again. Okay, so now we do the int, we clear, we have a nope, we halt, and we jump to 0xe. And 0xe is this line, which is exactly what we want. Okay, I think this might actually work. And then we have a lot of no-ups. And then at the end we have 55AA. Okay. So how do we test this? We need to spin up a virtual machine. So I can try this in QEMU, I think. I need to remember the syntax though. Let's see. Let's see, we do this. Okay. So you can run this in VirtualBox, or you can run it in VMware or ESXi, but I'm gonna do QEMU because I can run it in my terminal pretty simply. So let's see, we'll create a hard disk drive out of our os.bin, and we're gonna assign 512 megabytes, I guess, of RAM. Okay, let's go. Well, it is booting, but I don't see it printing anything. So we do this, move it into SP. BX is 0, AX is 0E78, and we run int 10. Let me just try something. If we skip this part, the trouble with operating systems is it's a little bit tricky to debug. Okay, now it's printed. Probably our we call the interrupt, and then directly after we clear the interrupt. So probably that gets us into trouble. All right. So now we can print one thing. But we want to print a string. Actually, I think the easiest way, since we have a lot of room, is to just repeat these instructions. Let's say we have a ctors print, and it takes a string, and it takes that string, turns it into an array, And then we map that array, and at each character we issue let's see, we need to copy into AX. So we issue ctors copy to AX, and we combine 0x0e with our x, and then we put it back together again. So something like this. And to this string we can actually add a new line. So it'll be R and N. Well, something like this will work, I think. So first we do this, and instead of doing this we take ctors ctors print, and we say we have a message. And we pass this message through. So let's say we have it here as well. And when we call this save to file, we want to give it our message. Something like this. By the way, to terminate QEMU, you do Control A, and then you release the keys, and then X. Alright, so let's run our node. Of undefined. So str here is undefined. So let's follow this thread. So we have a message. Message is this. When we call save to file, we pass on the message as the first parameter. returns into MSG. We call makeOS with this message. Here we have it, and we give it to part 1. Oh, we need to give it here as well. It's still 512 bytes. By the way, we can't just... It's not enough to just put it into AX. We also need to do the BIOS interrupt. So you need to combine those two. So when we print, we do this stuff. And to this return, we need to concatenate ctors dot BIOS interrupt, and then we join. Yeah, I think this should be the right thing. Still 512. OS. And what about objdump? We move a lot of zeros. Otherwise it looks okay. So let's see, we get the message here. And we concatenate this. So do they show up? I think that is 0A and 0D. No. So let's see, we put this to the string. We split the string up, character by character, in an array. We map through that array, and for each character, we return this string. But we need to turn this into a number. That's probably what's wrong. Okay, so now we give it 48, 65, 6C, and so on. That looks right. And we end it with 0D, 0A. Okay, this can actually work. Let's see what happens. Hello from JS. We have just created a small but the world's first operating system in JavaScript. And it is a real operating system that we can boot our computer with. So this is something you can put on your resume and in your Gits and your hubs and what it's called. And if you like this episode, make sure to subscribe, because there will be a lot of fun stuff coming forward. And also hit the like button if you like this episode. Thanks for watching. Thanks for today.